All right, guys. So, real quick, let's go over a few review questions from yesterday, and then we can hit some new stuff. Okay. Number one, guys, what is a wave?
It transfers energy.
Okay, it's a transfer of energy. Okay, and it's what causes it? A
Disturbance.
repeating disturbance. Okay, so a wave, a repeating disturbance that transfers energy. Okay, if it transfers energy through matter, it's called a
medium.
well, what's the wave called? A mechanical wave. And if it doesn't, then it's another type of wave. And we'll hit it right here. Okay. Number two, guys. What is carried by a water wave? Take a second. What is carried by a water wave, guys?
Energy.
C. Energy. Okay. A boat on the surface. Does a water wave move the boat?
No.
It moves it up and down, but does it change its location? It doesn't change position. Okay. Last and D. Water molecules. Do they move?
No.
They move up and down, but do they change position? No, they don't move with the wave, but they move up and down. Okay? Question 3, guys. Which type of wave does not need a medium? Take a second. What is it, guys? A. Electromagnetic. An ocean wave. It does require a medium. What's the medium?
Water.
Water. A sound wave. For humans, it requires a medium. What's the sound wave? Air. Okay. It can also travel through other things, but typically we're going to be talking about air. Okay, guys, we're going to have lots of different types of waves. We talked about mechanical waves, not mechanical, and we could have under mechanical we could have compression or transverse. Okay, and they can also differ in how fast they're moving, how much energy they carry. They can differ in how they look. Okay, and even a transverse wave can differ in that. Okay, so the first one, they can differ in how much energy they carry. A tsunami is obviously going to carry a lot more energy than that little wave I showed you yesterday with the paperclip drop, right? Okay, it's through the same medium, through water, and they're both transverse waves. Okay, however, it's a lot more energy there. Okay, we can also have other different characteristics. So how compact the wave looks, or how stretched out the wave looks. We could talk about how fast they're moving. Okay, so the first thing you need to know in order to identify these characteristics is that in a transverse wave, the high regions are called the crests, not the toothpaste. And the low regions are called the troughs. Okay, high regions crest, low region trough. This only applies to transverse waves. Okay, it does not apply to compressional waves. Okay, so does a sound wave have crests and troughs? No, because it is a compressional wave. Does a light wave have crests and troughs? No, because is it a transverse wave? No. Is a light wave a compressional wave? No. Okay, it's neither. So it makes light a little bit hard to visualize, but we'll talk more about light later. All right, so for transverse, crests and troughs. For a compressional wave, we're going to have compressions and rarefactions. Okay, same idea. Okay, we have still two regions, but since it's not moving up and down, it's moving back and forth, okay, we don't have crests and troughs, okay? So the compressed region, the region where everything's tight together, okay, that's going to be the compression. And the region where everything is spread out farther apart, it's going to be the rarefaction. Okay, so looking at that spring there, there's more space between the windings in the rarefaction, and there's less space between the windings in the compression. What's my next point? So that one's a little bit harder to visualize for me. Okay, the whole compression rarefaction thing. Easy way to remember it, guys, with a compression, that's where you see compressed particles. With a rarefaction, they're spread out, and so it's rare to see a particle. So rarefaction, rare to see a particle because the particles are spread out, and a compression, they're compressed, they're close together. Okay, just putting that into words, the more dense part, the compression, the less dense part, the rarefaction. Or putting it into writing, excuse me. We will often show a compressional wave like a transverse wave. Okay, so like in the poster in the back of the classroom, y'all see the sound poster? You see that's a transverse wave. Is sound a transverse wave? Starts with an N? No. Okay, so sound's not a transverse wave. So we'll often express a compression wave as a transverse wave. And what they mean there when they're doing that, guys, it's actually a graph, and they put pressure on one axis. And so if the pressure is increasing, then that would be this area up here. Instead of calling it the trough, that would be the compression. Okay, then the pressure decreases. Okay, now I have low pressure. That would be the rarefaction. Okay, so here, if this is pressure, the pressure would be everything crammed together. Okay, so tight together, more dense. Okay, and that would be the rarefaction. The particles aren't moving up and down. This is just showing high pressure, low pressure. Okay, so that's what we're seeing back in the back poster when they show that up and down. Okay, particles aren't moving up and down. That's high pressure, low pressure. Okay.
Can you go back in the slides?
Yeah, I'm gonna go back.
Go to the next one.
The last one, you mean? That one?
No, the other
That?
next one.
That?
That one. No, that's not it. That's the next one.
Well, we hadn't gotten to that yet.
It's like back. Like you had the compression thing. Like you just told us something different than the picture you showed us. This one.
Oh, okay, I see what you're saying. That's a transverse wave. Okay, what I'm showing you is sometimes we represent a compressional wave like this, but this is not a transverse wave. This is graphing the pressure. So in a compressional wave, okay, I would have, since these are close together, this would be high pressure. That'd be the top of the graph. And since these are far apart, that'd be low pressure, the bottom of the graph. You could also think of that as graphing the density of the particles, high density, low density. Okay, but that doesn't mean they're moving that way. Now, in a transverse wave, they're actually moving that way, but not in a compressional wave. Okay? All right, we have three different parts of waves that we're going to worry about. The first thing is how fast the wave is going. Okay, the speed of the wave to me kind of represents if you're clipped onto the front of the wave, how fast do you go? Okay, that would be the speed of the wave. More scientifically, if you're following a trough, how fast would the top of the crest? How fast would that crest be moving? That'd be the speed of the wave. Okay. The next thing, how spread out the waves are. Okay, so if they're really close together, then that's one thing. If they're really far apart, so how smushed the wave is. Okay, that's one category. Okay, and then the next category is how frequently they hit you. Okay, so if it's water waves coming, is it 10 seconds per wave, or is it 20 seconds per wave? Okay, how frequently are they coming by? Okay, that's the three characteristics that we're going to cover. The first one, guys, is called the wavelength. Okay, and this is the characteristic of how smushed or how spread out it looks. Okay, on a transverse wave, the wavelength is the distance from a crest to a crest or a trough to a trough. Okay, so on a transverse wave, crest to crest or trough to trough.
So the first one you showed us was the transverse wave. Like the very first one that you showed us, it was like that.
Yeah, that's the transverse wave. Okay, so if something has a, I'm going to come back to this slide. If something has a big wavelength, it would look like this. Okay, you see a large distance between a crest and a crest. If something has a small wavelength, it would look more like this. Okay, so a small distance from crest to crest. Okay, so big wavelength, small wavelength. So the bigger the wavelength, the more stretched out it looks. Okay? So that's for transverse waves. However, transverse waves don't have crests and troughs, so wavelength, let's think logically. If it's crest to crest, trough to trough, what's it going to be on a compressional wave? Okay, so it's going to be on a compressional wave, it will be from compression to compression or rarefaction to rarefaction.
Why are you going so fast?
Hmm?
Like you like speed.
Am I going fast?
We're like, you okay?
Okay, sorry. Hey, you just got to say the word.
I thought something was wrong.
Everybody done with that one? Any questions? I'm sorry if I'm going fast. I'm not intending to. Anything so far? Okay, so transverse waves, crest to crest, compressional waves, trough to trough. Crest to crest or trough to trough, and then a compressional wave, compression to compression, or rarefaction to rarefaction. Okay, so that's the wavelength.
You repeat that one more time.
In a transverse, crest to crest or trough to trough. In a compressional wave, it would be compression to compression or rarefaction to rarefaction. Same word to same word. Okay, so to draw out the compression wave is a little bit more difficult, but I'm gonna bite the bullet and do it. We get a good color. Okay, so in a transverse wave, if I have let's say I'm going to use particles. Okay, we'll call that the compression. They're close together, and then I have a rarefaction here. They're far apart, and then another compression here, close together. Okay, so we see a compression and a compression. Okay, so this would be my wavelength. Okay, that would be a long wavelength, stretched out. Okay, a short wavelength might look like Okay, so here I have a compression, a compression, a compression, and so I see a shorter wavelength there. Okay, so the shorter the wavelength, the closer those compressions are going to be together. That was a little bit harder to draw. Sorry.
Didn't you show us this yesterday?
The dot, I think I showed y'all that yesterday, but
So what's the rest of it?
what's the rest of what, huh? The lines? This line is, I'm just identifying that that's the compression, and so this would be the distance between the compressions. And so here I have two compressions, that's the smaller distance between the compressions. So they're closer together. So that would be a shorter wavelength. All right, so wavelength, the space between the waves. Okay, the next aspect of the wave we're going to talk about is called the frequency. Okay, and the frequency is going to tell you how often do the waves come. Okay, frequency is not the same as time. Okay, if the time increased, then that would mean lots of space between the waves, right? Okay, if the frequency increases, that means that it hits more frequently. Okay, so a high frequency will mean those crests and troughs are hitting you very frequently or very often, and a low frequency will mean they're not hitting you very often. Okay, so low frequency is low frequency. They're not very frequent. Okay?
What's the difference between that sound you have on your phone and a frequency?
That is a frequency. We're going to talk about that in a second. All right, you find the frequency of a transverse wave just by counting the number of crests that come by per second. Okay, so if 10 crests come by per second, then you have a frequency of 10. If 100 crests come by every second, you have a frequency of 100.
If it's like a high frequency, that's the kind you can't hear, right? Like it's
Well, it could be super. It could be that. Okay, so if it was a 30, okay, let me put this up here. So frequency expressed in hertz. That's the unit we use. So if it was a 30,000 hertz sound sound frequency, you can't hear that, and that would be because 30,000 times per second compression comes by, and your ears can't adjust to that. All right, so if I have a frequency of 10, that means every second, what?
10 crests.
10 crests pass. If I have a frequency of 1/10, what does that mean? Well, 1/10, that means 1/10 of a crest passed by, right? And so therefore, it takes 10 seconds for the next crest to come. So a frequency of 1/10 is 10 seconds per crest. A frequency of 10 is 10 crests per second. Okay? What would a frequency of 2/3 mean?
2 crests or 2.
2 crests in 3 seconds.
2 crests every 3 seconds. Okay, so a frequency of 2/3 would be 2 crests every 3 seconds. So the denominator tells you the time, the numerator tells you the number of crests. So 10 would be 10 over 1, 10 crests, 1 second. Okay, 1/5, 1 over 5, 1 crest, 5 seconds. Okay? That make sense? Okay, then the next thing I don't really want to talk about, so I'm going to skip past that. All right, the speed of a wave is the last category, the last thing I want to talk about. Remember, I said the speed of a wave represents if there was a like a bow attached to one of the crests, that would be how fast the bow's going. Okay, which the molecule wouldn't go with it, but if you could watch the top, how fast would it go? Okay, that's the speed of the crest, the speed of the wave. And this is not in the notes, but this is an important point. The speed of a wave does not change in a medium. As long as the medium is the same, then the wave speed is constant. So wave speed in a medium is constant. Okay, so one example is sound. Okay, sound, no matter how loud the sound is, no matter how high or low it sounds travels at the same speed. Okay, so if a car horn goes off and an opera singer go off and they both go at the same time, then you hear them at the same time. Okay, it doesn't matter how loud they are, doesn't matter what they sound like.
Is that V equals FA?
That's V equals, and we'll get to that in a second. Well, and by in a second I mean now. We'll go with green. Okay, so our equation is V equals F lambda.
Oh.
Yes, V equals F lambda. What now? Okay, this is just in case you are curious. This is spelled Lambda. Okay, lambda. Okay, and the way you draw it, guys, the easy way is just a line and another line. You could do that too, but that would take more time. Okay? All right, so V is going to be my speed. Okay, that speed is always measured in, well, what's the unit? Meters per second. Okay, F is my frequency. Hertz. It hurts when students don't remember that one, but fortunately you did. Lambda is wavelength. Wavelength is a length, so that should be measured in meters. Okay, so my wave speed, how fast the wave is going, is equal to the frequency times the wavelength. Okay, so let's do a little practice problem real quick. Sound in air always travels at 343 meters per second. Doesn't matter if it's a really high, if it's a high note, if it's a low note, if it's a loud sound, if it's a quiet sound. In air at room temperature, we're not talking about all that yet. It typically travels 343 meters per second. Let's say I have a sound with a frequency of 500 hertz. Okay, a frequency of 500 hertz would sound like, let me get out a little app. Okay, y'all hear that? That's frequency of 500 hertz there. Okay, so using that information, I can figure out what is the distance or what is the wavelength between the compressions that are hitting your ear. Okay, how far apart are they? Okay, so my equation, V equals F lambda. If I'm solving for lambda, I need to divide by F. Okay, so what I end up getting, guys, is lambda equals V over F. So my lambda here is going to be equal to 343 meters per second divided by 500 hertz. And I believe that is 686? Sure, whatever. I believe that's 0.686 meters. Okay, so what that means, guys, is that for that 500 hertz sound, okay, there is that much distance between each compression. Okay, so if you could take a picture, if you could get the picture of the molecules, you'd see some molecules close together right here, and you'd see some molecules close together right here. Okay, and in between you'd see them what? Far apart. Okay, so they'd be close together here, far apart in the middle. Okay, if I took the sound and I increased the frequency, it would sound higher. Okay, if I increase the frequency, what happens to the wavelength? It's going to decrease. Okay, so as I increase the frequency, that wavelength between the crests is going to decrease. Okay, so then if I have a high frequency sound, I might have a compression here, and spread out in the middle. Does increasing the frequency change the speed of the wave? Does increasing the frequency, making it sound higher, does that change the speed of the wave?
Yes.
No.
No, because the speed of a wave in any medium is constant. Now, but if the sound goes from air to water, does it change? Yes, because that's a different medium. Okay, so as long as it stays in the same medium, same speed. Okay? So what that means, guys, same thing with the pool of water. If I splashed and made a really big wave in the pool of water, it travels at the same speed as if I drop the paper clip in and make a very small wave in the water. Okay? No difference in the speed there, because it's the same medium. Okay? We good? Any questions on these few little topics here? Anybody? Yeah, I can. This one right here?